Welcome. We are on our last module. So we're going to go over the Chinese remainder theorem. Now you'll notice this is going to take the Euclidean algorithm, it's going to take congruences, and it's going to combine all of them together. So all we're going to do is Chinese remainder theorem. So to start off, I'm just going to start with a pattern. This theorem is about considering the remainders in different congruence classes, especially if we have 2 or 3. So to understand this, consider the integers mod 4 and mod 2. So integers 0, 1 through 10 along the top. And then I wrote in what they are, mod 2 and mod 3. You'll notice something, which ones overlap. So for instance, if I'm dealing with 0, notice the other one is also 0 or it's 2, it's 0 or it's 2, it's 0 or it's 2. Similarly, if I change colors to red, 1 is correlated to 1, 1's or 3, 1 or 3, 1 or 3. So that's one of our patterns. What else do we see? Well, when do they both have the same value? Well, they both have the same value here at 0 and at 1, then again at 4 and at 5 and at 8 and at 9. So these are all things we can start considering. All right, let's continue with this. Keeping that table, let's also compare the integers of mod 3 and mod 2. And here's the question: does the pattern we saw before continue? Why or why not? So just kind of pause the video and look at that for a second. All right, so if you looked at it, what did you see? Well, if I look 0, it corresponds to 0, it corresponds to, and it corresponds to 1. Strange. 1 also corresponds to the other numbers. So I don't have the same sort of thing where it's evenly broken up. Why is it different? Well, 1 might be the fact that the greatest common divisor of these two is not 1, whereas down here, common divisor of 2 and 3 is 1. So that tells us that our modular, whatever congruence class we're looking at, will help define a bunch of these things, especially when we have 2. What's their greatest common divisor? So this pattern actually leads us to a natural lemma. Namely, that if n1 and n2 have the same remainder mod b, and a divides b, then n1 and n2 have the same remainder mod a. So let me go back. So notice that, for instance, 3 and 7 both have the same remainder, mod 4. Well, that means they have the same remainder, mod 2, because 2 divides 4. However, notice just something totally different. 5, it also has the same remainder, mod 2, however, not the same remainder, mod 4. So that simply means we look at the larger one, and when we divide it, it will preserve the congruence. So to help prove this, here's a simple proof. We start off with supposing this if statement. So I'm going to start off with supposing all of this if statement. That n1 and n2 have the same remainder, mod b, and a divides b. And then by definitions of modular, it's actually a system of equations, or in other words, it's about remainders. So that means n1 is equal to some integer k times b plus the remainder r, and n2 equals j times b plus the same remainder r. Further, since a divides b, there's some d that ad is equal to b. So putting that together, n1 mod a is the same thing as kb plus r mod a, which is the same thing as r mod a. All because we can simply replace the kb is equal to k times ad, which is a times kd. So we can just simply swap out this portion is going to have a remainder of 0 when I divide it by a. All right. Similarly, You show the same thing for N2. Now notice that doesn't mean that they both have a remainder of R, rather they have the same remainder mod the lower value. So that's a critical thing to take into consideration. Now, let me show you how we can use that. Suppose that I have N is congruent to 1 mod 6. What are the possible values mod 4? Now, we could do this by brute force, literally by listing out all the numbers like we did before. And in that case, we actually only have to go up to N is equal to 11, because that would be, what's the least common multiple of both 4 and 6? Well, that's 12. However, we start at 0, so we go 0 to 11, and we count for those first 12 possible values. We can just look there. That's fine for this particular situation. I will tell you in other situations, don't do that. Those numbers will get really big. So instead, let's use the last lemma. Now, 4 does not divide 6. So you might be like, wait a minute, I can't do this. However, 2 divides 6. So by that last lemma, since N is congruent to 1 mod 6, then N is congruent to 1 mod 2. The 1 stays the same. If it had been 5 mod 6, that would be 1 mod 2, because 5 is 1 mod 2. So in this case, it's congruent to 1 mod 6 and congruent to 1 mod 2. And then we say, what are the possible remainders mod 4? Well, there's 0, 1, 2, or 3. Which of these is 1 mod 2? Well, 1 and 3 are congruent to 1 mod 2. Therefore, our solutions, N is either 1 or 3. Those are our only possible values for which we can get. Now notice this lemma, again, it's not like I used this directly, but I used it indirectly. All right, I'm going to pause the video here. I'm going to stop this video, come back to the second video as you learn about the Chinese remainder theorem.